Hi everyone. So let me introduce you to the last talk of the day with Maxime Rossi and Damiano Melotti, which will tell us everything about dissecting the modern Android data encryption scheme. Let's give them a warm welcome.
Thank you, and hello everyone. I'm really happy to see that so many people made it to the last talk. So yeah, let's get started. So today we're gonna talk a bit about Android data encryption, and it's gonna be me and Max, who's here next to me. We both work at Quarks Lab as security researchers, mostly on low-level software stuff. It can be Android or similar embedded things. And this research and also this talk was kind of triggered by a question we received after the work we did last year on the Google Titan M chip. This is a security chip that was introduced in Pixel devices to provide some security features. We were among the first doing some research on it, and we published a couple of presentations last year. And someone reached out to us asking whether we would be able to help them retrieve the data on their device after, I think it fell in water. So they were doing some hardware work, and they realized that the main SoC was dead, but the Titan M chip was actually working. So yeah, he was seeking for help. And well, our answer was no, we can't help, because the main SoC is still essential for disk encryption and decryption. But we were not exactly sure up to what extent this was actually true. So the objective was to find out, basically, find out why the main SoC is essential, how much the secure element, the secure chip is used. And then we wanted to find out, of course, how an attacker would try to break this feature. So assuming access to an infinite amount of vulnerabilities, or at least as many as you need, what can an attacker do to get the secrets out of an Android device? And in particular, what's the role of authentication? Are credentials actually used in the process? How does that work? So we're going to be speaking about two proof of concepts that we developed to show how to attack this feature using only software bugs. So we won't cover hardware or cryptographic things. And we're going to get started with a few elements of background so that we are all on the same page. So we're speaking about data encryption at rest, which basically means that feature that allows the devices to be stored encrypted in your file system in practice. So we are defending from an attacker that has full physical access to the device. The feature is actually quite fascinating. The first time I discovered it existed, it was quite cool to think that data is automatically decrypted and encrypted on the fly when you need to interact with the storage. And this is made possible on Android by two features that were one after the other, full disk encryption and then file-based encryption. That is the standard being used now. Behind those, we have DMCrypt for FDE and then FSCrypt for FBE. Now the difference between the two is not really interesting nowadays. It's required, FBE is required since Android 10. But giving a few more elements on the technology behind, so we said FSCrypt, the support ends up being in the Linux kernel and in the file system, ext4 in particular. So everything is at file system level. Basically, each file can be encrypted with different keys, but each of these keys are derived from a master key, while metadata are encrypted separately using another extension. So the fact that each file has its own key is actually essential to bring up a couple of interesting features that are present in Android. These are, for example, direct boot and multi-user support. Direct boot allows to have some files decrypted automatically when you boot the device, so that before the user authenticates, the device can still do some very basic things. And then you can have multiple users, also admin users and so on. And each of these users will have separate keys for their files. So this means we have two encryption levels. One is credential encrypted, so the one that protects user data and makes them available only after authentication. And then we have device encrypted data, which are instead automatically decrypted when we boot. So two encryption levels, two keys. The DE key is, as I said, automatically decrypted. There is some hardware-derived stuff that will come into the game, but we will mostly focus on the credential encrypted key, which is the one that protects the main data, the one that we are interested in. So just to give you a bit of better picture, data is the folder where applications are usually storing users' data, and before you authenticate, this is what you're gonna find on the devices. So the file names are encrypted. This is all garbage, basically. But there are some files that live in another folder, that's the one you see there, that are device encrypted, and these are the files you start on when you need to derive the actual credential encrypted key. So to reply immediately to one of the questions that we posed at the beginning of the talk, actually these files are combined also with the user credentials, the raw user credentials in the process. So it doesn't matter how many bugs an attacker has. As we said, we assume there can be as many as we want. You still need to go through brute forcing to get the final key. So since we're going to be talking about Trustlet, let's spend a moment to introduce what a trusted execution environment is. I'm sure most of you are already familiar with that, but so basically in modern OS features two operating systems. The main one, the one we are used to, in this case Android, runs in what we call the non-secure world, which basically allows to run an OS that can have a number of offer a number of opportunities to the user to change it. We can install applications and so on. But in parallel, we have a secure world where a trusted OS is running, an OS that basically can't be tampered with. There are trusted applications that are signed by the vendor and so on. The idea is that this secure world will have access to some resources that the normal world cannot access, so that there is this kind of isolated environment that we can leverage. And one of the services that relies on the TEE is actually the Android key store. So the feature in Android that allows to generate and store cryptographic keys. Now, keys are always stored encrypted in the Android file system in a form that is called the key blob. And there are three protection levels for these keys. We have software-only keys, TEE protected keys, which are the default, and hardware-backed keys, which is a level that is only available when a security chip is present in the device. But the bottom line is that the raw key material should never leave the protected environment that it belongs to. So in the case of a TEE key, the raw cryptographic material will only be accessible by the TEE. So to give you a practical example, what can happen with a key operation is that the normal world will need to do something with a key. So it will talk to either the key master TA for a TEE key or with the trusted chip for a Strongbox key. Sending the key blob and I don't know, for example, the plain text that it wants to encrypt. And the key master TA or the trusted chip will extract from the key blob the actual key, use it, and then return the result of the operation without ever leaking the key. Okay, so now that we have kind of put a few things into perspective, let's actually have a look at how the CE key is derived. And this is the case where there is no security chip. And like when we say it's complex, we actually mean this. So there are a lot of steps involving a lot of elements that end up being chained together. This is also probably unreadable. So we're gonna zoom in and have a look at some specific parts of the whole schema. And the first part is the one that actually starts with the credentials. So as I said, credentials are used in the process. And when we say credentials, we mean PIN, password, or pattern. If you think about it, when you boot your Android device the first time, you need to provide the authentication factor, even if you haven't rolled a fingerprint or a face authentication. That's why they're used here. So credentials need to go through a script. There is a key derivation function. All you need to know about it is that it's just slowing things down and making it costly to perform hardware attacks against it. So it's combined with this file that comes from the file system to create a token that will be then combined with yet another file to create what we call application ID. Now, this application ID is only used if authentication is successful. Otherwise, we don't move forward from here. So authentication is perhaps the essential thing at the base of FB. And so we're going to have a look a bit into how it's actually happening. In a device without a trusted chip, authentication is handled by the gatekeeper, trusted application. And this trusted application basically takes care of receiving what we call password handle. So the handle that is stored in a file, the one we need to try to match, and then the current attempt to authenticate. If successful, and this is actually a key point that is going to come up later, gatekeeper returns an authentication token. That is this signed token that will be used essentially by the system to prove that the user has also successfully authenticated. And then there is also throttling to prevent brute forcing, basically. So graphically, what happens is that the normal world will send a verify request with, as I said, the password handle and the current handle, so the current attempt. The gatekeeper TA will do something like an HMAC to verify if the current handle matches the password handle. If so, it will generate this authentication token using a specific key. Otherwise, it will just update its throttling counters, which will make brute forcing again impossible. Basically, it will remember whenever you try to authenticate, keeping logs on the time and so on, and it's very quickly prevents you from doing many attempts in a row. So going back to the schema, if you remember, we left it with the application ID. So if authentication is successful, we're gonna use this application ID for something, and that's what we're gonna have a look now. So the thing is, you don't want, as a design principle, you don't want to link the final key to the actual credentials, because what if the user actually changes their credentials, their password, for example? You don't want to re-encrypt the whole system. So there is one thing that lives in between, which is called synthetic password. And this synthetic password is stored also encrypted in the file system, but is actually, it needs to go through two decryption phases. One with a TEE protected key that is authentication bound, so it can only be used when the user has authenticated. And then a second decryption, which starts, uses the application ID basically as a key. So if we stop here for a second and take a look at this specific step in the key derivation phase, we can start thinking about how we can attack the whole system. And it's pretty clear that at some point we need to tamper with the trusted execution environment. We can do it in two ways. We have the key master trusted application, which will access this key you see on the left. So if we manage to tamper with the key master application, maybe we can extract this key, or we can tamper with the gatekeeper trusted application to bypass the authentication mechanism. So the final goal is to get to the synthetic password, and from there on, we will be ready to get the CE key. So now I'm going to leave the floor to Max, so that he's going to talk about our proof of concept, the first one.
Thank you, Damiano. So now we understand how the credentials are derived into the CE key, and how the trusted environment is used to to verify the credentials. So let's talk about the first proof of concept we implemented for this research. And here, our first goal is to have enough privileges on a device so we can retrieve all the files that are device encrypted and involved in the steps Damiano described like here you can see one of the files, the SP blob file, which is the green box on the top. And we will also need to look into the trust zone. Here we decided to look into the gatekeeper trusted applications. And for that, we need either multiple bugs, like code execution on the device, then a privilege escalation to the kernel to access all the files, and then to the trust zone. Or we can also use a single bug that will be early enough in the boot process so that we can bypass the secure boot and patch our way up to the kernel and the trusted environment. So for that, we decided to use these Samsung devices. These are Samsung A22. There are actually plenty of them, so we actually tried the proof of concept on these two devices. And the funny thing about this is how we discovered this bug. We were looking online for Unbrick tutorials, because it's often where you will find bugs, basically. And yeah, we saw some people doing stuff that you clearly cannot do without a serious bug. And actually, they were repackaging the tool that I will present next. So these devices are using a MediaTek system on chip that actually two different ones that are vulnerable to that have a critical vulnerability in the boot ROM. And yeah, on top of that, this they are running Android for sure. And yeah, the code is modified by MediaTek and Samsung. For example, you have the trusted OS that is Tigris, which is the trust zone OS designed by Samsung. So our vulnerability, actually, we didn't discover this bug. The tool MTK client that we are using here is developed by John Curler. The tool is super handy, and yeah, for use case it just works. So we won't give much details on the bug itself. Just for information, the bug impacts the protocols that are implemented in the boot ROM in order to unbrick or reflash the devices. In the case of MediaTek, it is called the download agent. But it's also implemented in a different way in other vendors. Now, we are using this tool to rewrite all the partitions we need to patch. And the tool is also doing a lot of work for us. For example, it can boot a modified preloader. So the preloader is a second bootloader after the boot ROM. It can boot a modified preloader and patch it to disable some checks that we will see later on, but basically the next checks of the secure boot. And yeah, so thanks to that tool, we can just bypass the secure boot. So let's take a look at the boot process of our MediaTek chip. So we have the boot ROM that verifies and boots the preloader. And then the preloader will do the same with, first of all, the ARM trusted firmware, which is actually the code running in the monitor mode, so the code running with the highest privileges on the device. It will do the same with the Tigris, which is the Trust Zone OS. And finally, it will load a third bootloader called a little kernel, which in turn will verify and boot Android. Now, this last step is more complex than just an arrow. There are several partitions involved, but yeah, we will stick to one step here for this presentation. But yeah, this feature is called Android Verified Boot version 2. Now, thanks to the tool MTK client, we can exploit the bug in the boot ROM, and the tool will automatically patch a preloader and start it. Then this will disable the verification of the next steps. So now we can patch Tigris because we want to patch the gatekeeper trusted application, and we can also disable the verifications into little kernels so that we can then root Android. So let's take a look at how we can patch this, and let's start with the little kernel. So this is a typical bootloader in Android. It was used a lot for a while now. I think only MediaTek is using it as a bootloader. And yeah, our patching strategy is quite simple. We simply follow an empirical approach. We first reverse engineer the bootloader. We try to identify where are the checks. we patch them, and we reflash the bootloader, and we try to see if we can boot a modified Android like that. And if it doesn't work, we repeat the process. So there is no, the firmware is closed source. The bootloader is a closed source. There are some sources that exist, but it was modified by MediaTek and Samsung. So the checks that we are interested into are actually not public. And there is no logs or things like this. So the only things we can have is have the bootloader print on the screen some JPEGs, like the one you see on the right. So this will give you an idea of pretty much where in the code you are. So so after some tries, we are able to disable completely the verification of Android. And to give you an example of what we have and what we want to patch here, we can see an extract. We have a dohash function that will then produce a hash of something that will be compared to a stored value, if you look at the memcompile line. There are plenty of ways to patch this, but we decided to simply replace the stored value by the hash variable so that it's compared with itself. Now that we patch little kernel, we can start to modify Android. And here, Android is based on two images. The first one is the boot image that contains a kernel and a RAM disk. And we have the super image that contains most of the system. It's a dynamic partitions, meaning that it contains other logical partitions. And yeah, here one of these partitions, the vendor one, contains all the trusted applications that will be then loaded by Android in the trust zone. So to root it, we are using this famous tool. You probably already know Magisk. It works super well. It's very simple to use. And it comes as an Android application that you install on the device. And it will patch the boot image. It will install some binaries like an SU binary that you can then use to elevate privileges to root. But when you do so, the user will be prompted and will be asked to grant or deny the permissions. And this will not work on our case because we cannot unlock the device. So we did few patches to make it work from a laptop and to always accept the privilege escalation. And then once we did this, we can boot a device. We can access it. We have access to all the files, and so we can read all the device encrypted files. Yet we cannot brute force the credentials because of this auth token Damiano mentioned. Since the keymaster task in the trust zone won't decrypt the intermediate value. So for this, we need to take a look into Tigris, the trust zone OS. So again, it is designed by Samsung, and you will find it on Exynos devices, but also on MediaTek system on chips. And here we have three images that contains Tigris. So the first one is the TEE image. We have the code for the monitor, the kernel, a binary called userboot.so. We have an archive called teaser that contains the root file system. And finally, we have the trusted applications and some drivers that are contained into the Android partitions. So if you want to learn more about Tigris, I invite you to read this very good blog post series by Riscure that describes with a lot of details the Tigris. So let's go back on this view of the boot and the verification of the images. So we have a preloader that will verify and load what's inside the TEE image. And then after the TEE boots, the userboot.so file is used to verify the teaser image, which in turn, there is a binary that will be executed, the root task that will verify the trusted applications whenever Android wants to use them. So it will ask to the trusted environment to load the application, and the root task will do the verification. So we want to patch Gatekeeper, and to do that, we need to patch all these steps, so the user boot file, the root task. And we will not go into the details on how to patch this, but it's pretty much the same, the same methodology as what we did for little kernel. So once we do that, let's take a look at Gatekeeper and how we can patch it. So on Tigris, the trusted applications are ELF files that are slightly modified. They have a footer and a header that you can remove to then open them in any disassembler. And there are a lot of symbols inside uh, because of the usage of libraries, also because of the global platform API that is it's a standard for the trusted environment, trusted execution environment that describes features like memory allocations, crypto operations, and so on. And so you will find a lot of symbols, and you will have the documentation for them. So it's very easy makes our life as a reverser easier. And you also have a reference implementation that is open source that is called Trusty TEE. It's now the trusted the TrustZone OS for the Pixel devices. And here you will find the implementation of trusted applications that are used in Android, like Keymaster and Gatekeeper. So let's take a look at them. And yeah, it works pretty much like what Damiano described. So we have two commands. The one we care about is verify. It's used to verify the credentials, and what it does is that it will perform an HMAC of the password handle, and it will compare the results to an expected value that comes from one of the files that are device encrypted. Now this HMAC, it is made with a key that is at some point retrieved by the gatekeeper trusted applications, and all the implementation of the HMAC is done inside the trusted applications. So what if we can leak this key that is used to perform the HMAC? Then we can perform the HMAC ourselves. And we can come with another strategy to brute force the credentials. Basically, what we have here, so we generate a new password. We HMAC the password handle. There is a bit of work to turn the password into the password handle, but it's doable. And then we have a value that we can compare it to the expected value. And this should be very simple to implement, and it should scale on bigger machines to be performant. So yeah, that's the theory, but in practice, it's not how it works. Sadly for us, in the Samsung Gatekeeper trusted application, they didn't use the HMAC. They used a function that is called KDF, which could be actually an HMAC behind. We don't know what's behind this KDF function. Because it's implemented in the library, but the library will call a driver in the kernel, and the kernel, according to some documentations, is supposed to call the crypto processor. Meaning that if we want to leak the key, first of all, we have all the steps. We need to reverse more things. We need to, at some point, we need to move forward with this research. We don't have infinite time to work on that. So yeah, we decided to go with a simpler strategy, which is patching Gatekeeper in order to always produce this auth token, because the auth token is not derived from the credentials. All right, so this is an example of what you have in here. I'm using Ghidra. So this is the function that performs the KDF. All the TEE underscore something are actually functions of the global platform API, and for which you will find documentation. And the only one that is different is the one TES derived KDF, which is the infamous KDF function. All right, so we can summarize our attack strategy as the following. Know that the auth token, whenever we enter any credentials on the device, the auth token will be produced and shared with the other trusted applications. So we will place ourselves between the two AES decrypts. We will read the output of the first one, and then we will generate new credentials to produce the application ID. And then we will try to decrypt them. And thanks to the Galois-Kunze mode, operatory mode that is used here with AES that performs authentication on top of confidentiality, we should know if the key is the wrong one, because the decryption will fail. So to do this, we are gonna hook a process called system server, which is behind the Android runtime, and we are going to use a tool that you already heard of, which is Frida, which is a great tool to instrument functions, and it works very well on Android. And so doing so, we can, as you can see on the screenshot, we can leak what here is called ciphertext by hooking this function, synthetic password crypto decrypt. And yeah, that's cool. So now that we have leaked this value, let's take a look again at the big picture, at the big schema. And for our brute force, we only care about the upper part. And yeah, the part on the right is we are hashing a file, sec this file to produce the hashed secret. This can be, we can retrieve the file, so this can be done only once. We don't really care about this for our brute force. We leaked the first AES decrypt, the result of the first AES decrypt, so we don't care neither of these parts. We end up with these steps that we can translate into this pseudocode. So first of all, we generate a new password, we script it to produce a token. Then we concatenate this token with the pre-hashed value, so the hashed secret from the previous slide. To produce the application ID, we hash it to produce a key, and we try to decrypt what is called here value from keymaster, which is the value we leaked from the first AES decrypt. We try to decrypt it with this key. So if it fails, we go back to step one. Here is an example of, we made a little Python script to brute force to implement that. So the script is really not optimized. Here you can find a very simple password into less than 20 seconds, but we are running that on a crazy VM with 30 cores or something like this. And the script can really be improved, but yeah, at least it works. So I'm going to show you a video, little video of this. I will put it in full screen. All right, so I'm booting the device here. It's a normal boot. Maybe I will speed up a bit. No, it's not working. Okay. Well, maybe like this. Cannot use the arrows. It's the demo effect, but with a video. Okay, so the device boots. So this is just to show that it's a normal device, but you can't really tell. You need to trust us. You didn't see that. At some point, I need to enter a PIN, so the device is protected with a PIN code. All right. Then we shut down the device. So on this device, we need to short 2 pins to enter in this mode to download, access the boot ROM vulnerability. On the other one, we don't, but we bricked it before recording the video, so we had to stick to that one. So now I'm gonna run the script, which in background will first call MTK client. Let's move a bit forward. All right, here I'm dumping the images I want to patch. And I was a bit too fast. Yeah. Then I'm using Magisk to patch the boot image. Then I'm going to patch the other images. And here I'm just flashing them back on the device. So once it's done, I just start the device using, again, the MTK client tool to bypass the secure boot. You can see the Quarks Lab logo, meaning that something changed in the firmware. Maybe I'll speed it up a bit. Yeah, here I am dumping the files that I need to perform the brute force. Then I will start Frida. Yeah, so we leaked the the intermediate value from the first AES decrypt, and now we can start the brute force. So here I will move. Okay, so we found it. Woo! So the password is 1106, like the date of today, and the throughput is not really good because the script is not very good. Also because I'm recording at the same time on my laptop. So yeah, Ah. Okay, that's Damiano's laptop. Okay, yeah, cool. Yeah, quickly, the end is that I first show you that I have access to the files, but they're all encrypted. Then I just enter the password that I discovered, and you should see we have access to the files. Yeah, it worked. Okay, so this is how you can do when the verification of the credential is done with Gatekeeper and the trust zone. But what about the security chips? So let's again take a look at this big picture, the architecture view. So the architecture of the main system on chip is exactly the same. We have the non-secure world, or the normal world that will run the Android. We also have a trust zone environment, the secure world, that will run an OS and also an application like Gatekeeper, not Gatekeeper, but Keymaster. And on top of that, we have a chip on the left that is completely separated. Well, it depends on which device, but on the one we will study, it's completely separated in terms of hardware. And here again, you will have security features implemented. So we decided to focus on the Titan M chip because we already know it, and we discovered bugs that we already presented and reported. And yeah, this chip has been introduced by Google in the Pixel phone starting from the Pixel 3. We are going to show you a proof of concept that works on the Pixel 3a, but it should work on all the Pixel devices that have the Titan M version 1. Because yeah, they introduced the Titan M version 2, which is really enhanced in terms of security, starting from the Pixel 6. Now, this Titan M is based on ARM Cortex-M3, and most of the code is divided into tasks. We have a Keymaster task that is the backend of the key store, and when it relies on the security chip, it's called Strongbox. And funnily enough, it is not used when it comes to data encryption. Instead, we have another task that is called Weaver that is used for data encryption to store tokens. Now, Google introduced this security chip, according to them, to reduce the attack surface and mitigate side channel bugs. Like, this is due of the fact that the trust zone, the secure world and the non-secure world will share hardware resources like the RAM, like the CPU cache, and it was shown across plenty of researches that it was possible to mess with the secure world from the non-secure world. Here we give an example of attack like raw hammer that allows to do that. Titan M is also tamper resistant, so it has security features implemented in the hardware level. For example, there is a shield that is active, so if you open the chip to access the die, it should be detected. And so the hardware is isolated. It's completely different than from the main system on chip, and the firmware as well. So this is how the chip communicates with the main system on chip. So how the Titan M communicates with the main system on chip, and it uses the hardware bus SPI. On the Android side, you have a kernel driver that will handle the low-level protocol. It will forward everything to a daemon called Citadel D, which will act as a proxy. And we have it's called here the HAL for hardware abstraction layouts, which are the daemons implementing the application part of the protocol. There are most of them using protobuf to do this. And whenever you have an application that needs to do something like generate a key in the Titan M, it has to call the HAL daemon. The messages will go all the way up to the Titan M. So this is the memory layout of the chip. And what is interesting for us today, first of all, is that you can see the arrow and RW, which are the images. You have a loader and the firmware. And all the addresses you see are physical addresses. There is no virtual memory here. Everything is static. And there is not much RAM, meaning that the code is directly executed from the flash. So all these addresses are the ones that you will find in the code. And we also have the two regions called SFS, which here you will have a file system that is used to store persistent data, and actually Weaver is storing all its secrets here. So now let's focus on Weaver. We can compare it to a dictionary of pairs of a key value. The keys will be stored in one of the file systems, the values in the other. And it's a very simple task. It does, there are 4 commands. You can basically read-write the slots. You have here an example of the read command, the protobuf definition of the read command. So whenever the system wants to read a value, it has to provide the slot number, and it has to provide the key, which is a byte array of 16 bytes. And if everything matches, the chip will reply with the value, which is also a byte array of 16 bytes, plus some other informations like an error code and the throttling, because the throttling is also implemented here, meaning that we cannot just send any keys possible to get the value. And let's take again a look at this big picture, this big schema, which is here slightly modified to take into account Weaver. Actually, it's very similar to the previous one. If we zoom in on the upper part, which is the only one that differs, we can see that the credentials are turned into a token using the script function here again. The only difference is that then the token is used to produce the key with an hash function that will then be sent to the security chip, along with the slot that comes from a file that is device encrypted. So if it matches, the chip will return the value. And then this value is hashed to produce the hashed secrets, and token and hash secrets are concatenated together to produce the application ID. And starting from there, it's exactly the same as what we presented before. Now I will let Damiano continue with the actual proof of concept.
Thank you. So we're gonna show you a bit how to attack the schema this time when a security chip is involved. And the thing is, unlike previously, we need for sure at least 2 bugs, because the chip is running its own OS. It's independent, completely independent from Android. So when Google said they would decrease the attack surface, well, that's actually true. So we consider actually that the device is already rooted. We can do it with Magisk, and it's just for our own convenience. And then we have an exploit for the Titan M chip. This time the vulnerability was actually discovered by us and was covered in one of the presentations we did last year. Just a few words on the vulnerability. It's an out-of-bounds write of just 1 byte that can be set to 1. It was kind of a ride to turn this very tiny primitive into an actual code execution exploit. And if you're interested, go check out our blog post on this. But anyway, being the memory fully static, we can cause a bigger corruption by overwriting a global field, and this basically gives us the code execution exploit we were looking for. But actually, it is not really too much a matter of executing code of the chip on the chip that we are interested in, but it's to be able to read its memory. So basically, what we did was we built a client to communicate with the chip that's called the NOS client. And it's like used normally to send commands. But on top of that, we built a leak feature that uses the exploit to read arbitrary memory in Titan M. So with this, we know that somewhere in memory we have the Weaver slots and the values, so they must be stored somewhere. And with a bit of reverse engineering and a bit of debugging, we managed to find where the keys and values are stored and to leak them. You can also use Weaver write and read to add new slots and then try to look them up in memory. This ends up not being too hard. So if this becomes possible, the attack strategy is even simpler than previously because we just need to leak the Weaver key, and without thinking about that AES decryption we saw earlier with the synthetic password, we just need in this moment to brute force on the leaked Weaver key that we managed to extract. So the attack looks a bit like this. We generate the password, we script it, and then we compare it with the hashed token and the key that we leaked. So yeah, here you see the throughput again. Don't don't think about this number too much, because they are just coming from a very non-optimized script, and most importantly, probably a real attacker would use GPUs, which is not something we did. So we have another demo, another video, another awkward moment where we can't play it. So the thing in this case, we have again a terminal and the Pixel 3a open. I'm showing the data directory that is encrypted, and I am now running the exploit after stopping the Citadel driver. That is the driver that talks to the chip to leak this this value that we need for our brute forcing strategy. So let me just stop for a sec. Here, of course, we knew the right offset, but to show you a bit how we found it, this is a 0x100 bytes, and you can see like in this part of the memory what might be a SHA digest, right? I mean, all the rest is null bytes. There's a bunch of A's which come from the tries we did, so it was not particularly hard. So we get to that buffer that we need to extract. And what is left to be done is to extract the files we need to start from, like Max did in his case, and just go back to the main laptop, extract these files, reboot the device. This is needed just to kind of restore it in a normal state after we ran the exploit, but it might not even be strictly needed. And then we go launching the brute forcing script with the file we extracted and the key we leaked from the Titan. So this again is gonna take a while, also because OBS was eating my cores, but at some point, hopefully, you should find out that the code is again 1106, and that allows to unlock the device successfully. Okay, so time for the conclusions. So we talked a bit about this FP feature on Android, and I think one of the nicest takeaways is that it's actually a really well-designed feature. It's really interesting to see how ingredients are coming a bit from everywhere and are combined together in a way that you always need all of them to get to the end. So we have some files that are owned by privileged users. We have keys that come from the trusted execution environment, for which you need authentication tokens. So you need to tamper with the TEE. And finally, when a trusted chip is available, it is used not directly for the key, so not with the key master task, but to extract a value that is stored securely in this Weaver dictionary. So we need multiple bugs to break this feature, or a very powerful one in a device that can be compromised with just a bug. So in the case of a Samsung device, a boot ROM bug was enough. In the case of the Pixel, at least 2, but probably more to get to root on the phone, were needed because of the separation between the main application processor and the Titan M. But still, you need to brute force the credentials. So yeah, if your password is very long, like the one I'm writing here in the slides, well, it will take perhaps a few seconds to unlock your phone, but it will be really hard to guess. And with that, thank you very much, and we are happy to take any questions.
So how hard was the gatekeeper code to reverse engineer? Because I know a lot of it is open source, like the daemon is actually open source, part of the Android platform, but I don't know about the rest of the code.
Yeah, so it's not public. The trusted application for Tigris. I think there was a leak 1 or 2 years ago of that. Yeah, contains a lot of things from Samsung, including an implementation of the gatekeeper trusted application for Tigris. But it's an old version, so here we really had to reverse engineer it. And yeah, there are plenty of symbols. So it's not really hard, actually, to reverse.
So the only part that is open source, that the big part, is all the schema you have seen comes from Android, and that is available in open source. That is code.
On one of your slides, I think you had the Titan M, and you had a diagram showing it was connected with the spy bus to the non-trusted part. Have you done any work to know if they actually secured everything that's going on that bus, or you purely stayed at the software level?
Everything is non-encrypted on that bus. And yeah, we did, when we presented last year our research on Titan M, we did some man in the middle on the SPI bus, so we could sniff everything that was passing through.
Okay, good.
Thanks.